GraphQL Security Essentials is all about understanding the fundamentals of GraphQL and ensuring you can implement it securely. So, what is GraphQL? GraphQL is an open-source query language for APIs created by Facebook in 2012. It provides greater flexibility in how APIs are built and called, allowing developers to specify exactly what data they need. This flexibility not only streamlines the data retrieval process, but also optimizes network usage, making API requests more efficient. As we dive deeper into this course, we'll explore the key aspects of GraphQL, highlighting why it has become a popular alternative to traditional API methods like REST and SOAP. The importance of GraphQL can't be overstated. As an alternative to REST and SOAP, GraphQL offers a more efficient way to manage APIs. Industry giants like GitHub, PayPal, and Intuit have adopted GraphQL, highlighting its growing significance. One of the key features of GraphQL is its ability to fetch and manipulate precise data. Unlike REST, which often returns more data than needed, GraphQL allows you to specify exactly what data you require, reducing overhead and improving performance. This level of granularity provides a streamlined and effective approach to handling API calls. Understanding GraphQL will enable you to build more responsive and flexible applications, making it an essential skill for modern API development. Now, let's move on to the common attacks in GraphQL. It's crucial to understand these vulnerabilities to ensure the security of your API. Injection attacks are a significant concern in GraphQL, just as they are in traditional REST APIs. There are several types of injection attacks to be aware of. 1. SQL and NoSQL injection. These involve manipulating the backend database queries through malicious input. An attacker might attempt to execute arbitrary queries, potentially gaining unauthorized access to data. 2. OS command injection. This type of attack occurs when the attacker tries to execute operating system commands via the API. The consequences can be severe, including taking control of the server. 3. SSRF and CRLF injection. Server-side request forgery, SRF, can trick the server into making unwarranted requests to unintended destinations, potentially leaking sensitive data. Carriage return and line feed, CRLF. Injection can manipulate the way data is handled, leading to vulnerabilities like HTTP response splitting. To mitigate SQL injection, for instance, you can use parameterized queries. A command example would be SQL insert into users, username, password, values, door. This approach ensures that the parameters are treated as data and not executable code, effectively preventing injection attacks. By understanding these common attack vectors, you can take steps to secure your GraphQL API against such threats. Denial of service, DOS attacks, pose a significant threat to any API, including those built with GraphQL. These attacks can render your API slow or completely unresponsive, consuming excessive resources and leading to potential downtimes. To mitigate the impact of DOS attacks, there are several techniques you can employ. 1. Depth limiting. This involves setting a maximum depth for queries, which prevents attackers from nesting queries to a level that would exhaust resources. 2. Amount limiting. By limiting the number of fields that can be requested, you can protect against overfetching data in a single query. 3. Query cost analysis. This technique involves evaluating the cost of each query based on its complexity and requiring higher authentication levels for more expensive queries. This ensures that heavy queries are executed only by trusted users. Implementing these mitigation techniques can help maintain the performance and reliability of your GraphQL API in the face of potential DOS attacks. In this slide, we will be discussing best practices in GraphQL security, specifically focusing on input validation. The first practice to consider is using an allow list strategy. This involves creating a predefined list of acceptable inputs, thereby reducing the risk of harmful data being processed by your system. Next, it's crucial to use GraphQL-specific data types. GraphQL offers built-in types that help enforce the format and type of the data, preventing erroneous or malicious data from being executed. Finally, implementing custom validators can provide an additional layer of security. Custom validators allow you to define your own rules and procedures for how the inputs should be verified. This is especially useful for specific types of data that require unique validation logic. These practices collectively ensure that the data entering your GraphQL API is well-formed, secure, and reliable. This fortifies the integrity of your system and defends against potential security vulnerabilities. Input validation in GraphQL is crucial because it helps prevent injection attacks and ensures data integrity. By validating inputs, we can safeguard our APIs from potentially malicious data that could compromise our systems. To implement input validation effectively, consider using strategies such as the allow list approach and employing GraphQL-specific data types. Additionally, custom validators can be implemented to enforce strict validation rules. For example, you can create a custom scalar type to validate inputs such as email addresses. Here's a command showcasing how to implement this for an email type. JavaScript const GraphQL scalar type equals require GraphQL. Const validate email, new GraphQL scalar type, name email, serialize value, validate value, custom email validator. This command defines a new GraphQL scalar type named email and applies a custom validator to check the validity of the input, ensuring that only properly formatted email addresses are accepted. On this slide, we're going to discuss strategies for preventing denial of service, DOS attacks in your GraphQL API. DOS attacks can overwhelm your server by sending a high volume of complex or deeply nested queries, potentially causing performance issues or downtime. To mitigate these risks, we have several effective strategies. 1. Depth and amount limiting. Implement restrictions on the depth and number of fields in a query. This prevents excessively nested queries that can consume significant resources. 2. Pagination implementation. Use pagination to limit the amount of data retrieved in a single query. This way, you control the size of the datasets being processed and returned. Reasonable timeout. Apply reasonable timeouts to query execution. If a query takes too long to process, it can be halted to free up resources for other requests. Together, these techniques help ensure that your API remains robust and responsive, even when faced with potentially malicious or overly complex queries. Now, let's look at an example of how to implement depth limiting in JavaScript for GraphQL. Depth limiting helps prevent overly complex queries that might overwhelm your server. Here, we use the GraphQL depth limit package to restrict the depth of the query. First, we require the GraphQL depth limit package. JavaScript const depth limit require GraphQL depth limit. Then, in the middleware for our GraphQL server, we use GraphQL HTTP and specify our schema. We add a validation rule with depth limit 3, which sets the maximum query depth to 3. JavaScript app/q GraphQL HTTP schema validation rules depth limit 3, max depth of 3. This ensures that any query with a depth greater than 3 will be automatically rejected, thus adding a layer of protection against denial of service attacks. In this slide, we're introducing the concept of query cost analysis in GraphQL. Just like depth limiting, query cost analysis helps in maintaining the performance and security of your GraphQL endpoint by restricting overly complex or expensive queries. In this example, we incorporate the Graph Cost Analysis library into our server setup. The cost analysis function is used to define a maximum query cost, which in this case is set to 100. By adding this to the validation rules array, we ensure that any query exceeding this cost will be flagged and prevented from execution, thus protecting our server from potential abuse and ensuring fair usage of resources.
In this slide, we're going to discuss access control in GraphQL, focusing on general data access principles. Firstly, it's critical to validate the requester's authorization. This involves checking whether the user making the request has the requisite permissions to access the specific data they are requesting. Secondly, we need to enforce role-based access control mechanisms. RBAC helps in assigning permissions based on the roles assigned to users within the system. This way, we can ensure that users can only perform actions or access data that their role permits. Lastly, we must take steps to prevent insecure direct object references (IDOR) issues. IDOR vulnerabilities allow attackers to access unauthorized data by simply tampering with the input. Implementing robust access control checks can mitigate this risk effectively. Together, these principles form the backbone of a secure GraphQL access control strategy.
Here we provide a practical implementation example of role-based access control, RBAC middleware, in a GraphQL environment. This example involves creating an isAuthenticated middleware function. The middleware function wraps around a resolver. It checks if the user is authenticated by inspecting the context user property. If context.user is not present, it throws an error stating not authenticated. If the user is authenticated, it proceeds to execute the resolver function with the provided arguments. Let's break this down. 1. Function declaration. JavaScript const is authenticated equal resolvers, parent, args, context, info. 2. Authentication check. JavaScript if context.user, throw new error, not authenticated. 3. Resolver execution. JavaScript return resolvers, parent, args, context, info. By implementing this middleware, we ensure that only authenticated users can access certain resources or actions in the GraphQL API. This is a fundamental step in securing your application and enforcing strict access control policies.
Disabling insecure defaults is a crucial step in securing your GraphQL APIs. One significant measure is to disable introspection in production environments. Introspection is a GraphQL feature that allows clients to query the schema and discover types and fields, which is great for development but poses security risks in production. To do this, we can use middleware configuration by applying GraphQL HTTP from the Express GraphQL library. Here's an example implementation. JavaScript app.use/GraphQL, GraphQL HTTP, validation rules, no introspection, graph equal false. In this snippet, we're setting graph equal to false to disable the GraphQL browser IDE and including no introspection as part of the validation rules. This prevents clients from querying the schema itself, thus reducing potential attack vectors. By incorporating these changes, you significantly improve the security posture of your GraphQL API in a production environment.
Moving on to mitigating batching attacks, an important security measure in our GraphQL implementation is to limit the size of query batches. Batching allows multiple operations to be sent to the server in a single request, which can be leveraged for brute force attacks if not properly handled. To prevent such attacks, it is crucial to restrict the number of operations that can be included in a single batch. Here's an example of a command to limit batches effectively. In this case, we set a maximum batch size of 5 operations. JavaScript const max batch size equal 5, app.use/GraphQL, GraphQL HTTP, req next. If req.body length, max batch size, throw new error, query batch size exceeded, next. This script ensures that if a request's batch size exceeds the defined limit, an error will be thrown, preventing the execution of the excessive operations. Implementing such controls is a critical step in fortifying your application against potential brute force attacks in a GraphQL environment. When it comes to securing your GraphQL endpoints, using the right tools can make a significant difference. On this slide, we focus on essential tools for GraphQL security. Firstly, let's talk about InQL Scanner. This tool helps in automatically generating queries and mutations. It's extremely useful for testing and verifying the security of your GraphQL API, as it can dynamically create multiple kinds of queries to interact with the schema, helping you identify potential vulnerabilities. Next up is GraphQL. This is a developer-friendly tool designed for schema exploration. It allows you to visualize and interact with your GraphQL schema, making it easier to understand its structure and to query it effectively. By leveraging GraphQL, you can ensure that the schema you expose adheres to your security requirements and best practices. Utilizing these tools can significantly bolster your efforts in securing your GraphQL endpoints and ensuring a robust and fault-tolerant API design. The current slide demonstrates a practical example of how to use InQL Scanner for query generation. This tool can be highly effective for automating the creation of queries and mutations in a GraphQL environment. The command shown here, python3inql.py t8/example.com/GraphQL, uses a Python script to target a specified GraphQL endpoint. By running this command, InQL Scanner will analyze the schema and automatically generate queries and mutations, simplifying the process of exploring and testing your GraphQL API for security vulnerabilities.
Moving on, let's discuss further resources for advancing your understanding of securing GraphQL APIs. Documentation and guides are invaluable for deep dives. Consider starting with the OWASP GraphQL Cheat Sheet, a comprehensive resource for understanding common vulnerabilities and countermeasures. For practical insights and real-world examples, I highly recommend the blog post titled Protecting GraphQL APIs from Security Threats. This article provides actionable advice and best practices. Lastly, to broaden your comprehension of security perspectives, the GraphQL Security Perspectives module is an excellent structured resource. These materials will give you a solid foundation and keep you informed about the latest security trends and strategies specific to GraphQL.
In conclusion, there are several key takeaways to ensure the security of your GraphQL API. First, apply rigorous input validation. Validate and sanitize all inputs to prevent common security vulnerabilities. Second, implement depth and amount limiting to control the complexity and size of queries, which helps prevent abuse and potential denial of service DOS attacks. Finally, monitor and control access effectively. Regularly review access controls and keep a close watch on API usage to detect and respond to potential threats promptly. Now that we've covered the key takeaways and best practices for enhancing the security of your GraphQL API, let's focus on some final thoughts and next steps. Start by experimenting with different security tools to find what works best for your specific environment. There are many tools available that can help you identify vulnerabilities and enhance your security measures. Moreover, it's crucial to regularly audit your GraphQL API. Periodic audits will help ensure that your security practices are up to date and effective against new threats. These steps will help you stay proactive and maintain a robust security posture for your GraphQL APIs. Thank you for taking the time to go through this course. I hope you found the content both informative and useful for your learning journey. If you enjoyed what you learned, feel free to leave a like and share your thoughts in the comments below. Your feedback helps us improve and create better content for you. Make sure to subscribe to the channel so you don't miss out on future courses. Finally, don't forget to share this with your friends and colleagues who might also benefit from the information. Happy learning!